So we'll do this, and then after that, if you finish with time to spare, because you have the first period to do this, if you finish with time to spare, which you can be working on any of those word problems from yesterday, just trying them. You don't have to have those done today because we're going to be going through those today, but that is something that you could be working on afterwards. We will be dealing with that during second period, okay? All right, so it is time for the quiz. Time for the quiz. I'm just telling my online kids. Quiz found in Google Classroom. Read instructions. Shabow. Okay, so there's that. I can do that. Boom, exit that. Close this. La 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 la. You guys watching the weather forecast at all? Next week's looking like it could be quite the week for us. So, okay. Woo! All righty. It'll be a good one. You guys are going to be fine. Take a deep breath. All will be fine. You guys, and then we'll just real quick flip through this. So, number one, that's a gimme. 2, we did it in class one day. It wasn't on your last sheet, but we did that in class. 3 is expand, 4 is condense. They're not solving anything on 3 and 4. Back to the equation. I did not put anything like that one yesterday where you had like 2 to the x equals 7 to the 3x minus 4. There's nothing like that on there. Everything here you're capable of. Also, notice it says solve exact, give an exact answer followed by an approximate answer rounded to the nearest thousandths. So for each of these, exact and then the approximate answer to the nearest thousandths. Okay? Good luck. I think you guys will do well on this. I really do. That here. Here. if you end up finished with it, you can just turn it in at any time.
Hey.
I had to make an answer key for mom first, so it'll be next
Oh,
week.
what's that?
I'd like to buy that as a place to go away to.
Where is that?
Down in North Colorado, close to the Ohio River.
Oh my gosh.
I would love
Look
to.
at the cool siding.
I know, wouldn't that be cool?
So onliners, you should be finding the word problems. Okay, make sure you find those word problems. They were posted the other day. And the first one talks about Mrs. Borcher. So please find that if you would. We'll start looking at these. I'm going to find it here. There we go. Stop. All right. So some of this, a lot of this will be review as far as setting up equations. Now, remember, I also gave you guys this. You guys got this, right? Remember this? Had all the different kind of like how you can apply exponential functions and so forth. Okay. So if you need this, you can have that out at any point in time. Before I do anything else with this, we'll start to look at some of these problems. I have a quick question for you. If I had the following, let's say I had the following problem, okay? Is this, by the way, exponential growth or decay? Growth. How do you know it's growth? What's greater than? The thing in the parentheses, that's the what? The value of what? That's the what? B value. It's the the what? What do we call that value? Being raised to a power. Base. It's the base. Base is greater than 1. It's growth. Base is between 0 and 1. It is decay. Okay, great. Now, we did this a while ago, so I'm coming back to this right now. Can anybody tell me by what rate that's growing? 3%. So the growth rate is 3%. The growth factor is 1.03. They're two different things. Factors and rates are two different things. Remember that. Okay, now, I would like for you to see if you remember how to do this. Write as a continuous growth function. See if you guys remember how to do that. We did that in here right before we started exponential and logarithmic functions. Actually, we did that in here when we were dealing with that. Okay? How do I write that as a continuous growth function? We did this right before that. And what's the model for a continuous growth function look like? What's the general model? No numbers. Y equals A times E to the RT or RX, variable don't matter, right? Okay. How did I know if this, I know how this is growth or decay, it's all about the value of B. How do I know if this is growth or decay? What was the rule on the continuous growth functions or continuous decay? How did we know if it was growth or decay? What told us? R. What about R? If R was what? Yeah, if it's positive or if it is negative. If it's positive, it is growth, and if it's negative, it is decay. All right. What do you guys remember? Think about the how. Do you remember how we did this? So I know for this model, it's going to be what? Y equals, what's A? 580. That doesn't change, right? Times E to the RX. What I don't know is R. Okay, and I'm going to bring this one down right below it. My original one was Y equals 580 times 1.03 to the X. Look at those. Remember what we said. Look at those. This has to be equal or equivalent to that. Remember, this is 580 times e to the r raised to the x. It's the same thing. So e to the r has to be this. So I'm just going to write a real quick equation. E to the r equals 1.03. How did I have you guys solving that in the past? Graph it. You don't need to graph it anymore. Now you do what? You use a logarithm for it instead. So now I can go to continuous quite easily. For this one right here, r is just going to be the natural log of 1.03, whatever that is. Okay? So this is going to make it real easy to change to a continuous model. And I won't even have to round it. What? I won't even have to round it. This one right here, guess what it would be as a continuous? 580 times what? E. What is r? The natural log of times what up here? X. There it is. And by the way, I want you to look at it, by the way. What's the answer to this? X. What? So this base and this base are the same. Are these bases the same? So what is this? What is this equivalent to? 1.0. Okay? But I could leave it like this, and now I actually could get, I wouldn't have to round my answer. There's no decimal rounding needed right here. So I'd be more accurate if I leave it like that. All right. Oh, wow. Amazing stuff. Amazing. Okay. So that was something we did right before we did logarithms. We talked about how would I find this value of r. Okay, we did it by graphing. All right, now let's go back to our word problems. Here we go. Okay. So the first thing I want you to do, I don't know what you've done with this. I'd like you to go through and read each one and decide, okay, is it going to be growth or decay? And maybe, and there might be a question where it's not either one. And I'm not sure anymore. I haven't looked at this since I gave it to you guys. So everyone's looking at number one. Is this growth or decay? This is decay. I'm just going to put left of it a big D for decay. Okay, great. Number two, what is it going to be? What's that? I heard both now. So let's see what's going on here. At sea level, the pressure is 14.676. In Mile High Stadium, which is in Denver, which is 5,280 feet above sea level, the pressure is 12.2. So as X is increasing, what is Y doing? Decreasing. So is it decay or growth? It's decay. All right. Number three, let's go skydiving. Da, 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 da. Oh, you're going to use your answer in number two for this. So this is not, is it growth or decay? You're applying number two. So we'll come back to that. All right, look at number three. Growth or decay? Decay. Five, oh, five's going back to here, and it's asking for continuous. That's why I just reviewed that with you. Here, this is a regular model. This is a continuous model. So we'll do that in a second. Six. Okay, we have to talk about number six. We have not done a problem like this. Okay? So you can follow as I'm reading it. It says a fossil was found in the field hockey field, which many believe could be from the Jurassic creature, the fire raptor, which used to hunt this land. After testing the bone, it is found to still possess 1.8% of its carbon-14, carbon dating, okay, to find out how old something is. Given that the half-life of carbon-14 is 5,727 years, how old is the bone? And then it says if the Jurassic period is about 150 million years ago, could the bone actually be from a fire raptor? And then it says right here, half-life model. Okay, that is on your gold sheet. It's on the gold sheet and it's on the back. Middle one. Okay, and you'll see there's one that says y equals a times 1/2 raised to the t over HL. Okay, or maybe it's x, I don't know. X on this one, I guess it is. Right? Doesn't matter what that is. Now, what does half-life mean? Half-life means how many years does it take before half of an item disappears? Okay? So that's a lot of times used with radioactive isotopes. Okay, in chemistry, maybe you've heard about half-life. So it's how long does it take? It could be years, it doesn't have to be years, it's time. How much time does it take before half of an item is gone? That's why the base here is automatically going to be 1/2. Automatically going to be a half because you're always taking half of it. Now, what does this mean? HL is the half-life of the item. HL, that's this right here. HL in this problem is 5,727 years. That is the half-life for carbon. So let's say that 5,727 years pass by. How many half-lives has it gone through? 1. So that's what we have to put up here. So this value on top is how many years or how much time has passed by relative to what the half-life is. And this tells you how many half-life cycles has it gone through. Okay? So if I made it 5727 or 5727, it'd be 1 half-life period has gone through. Okay? So that's the idea on this half-life model. Okay, so we're going to be doing that one. And then the bottom one down here, of course, is a what? Newton's law of cooling. Now here's the deal. I want you to go through and write your functions for these to start. Then anything you're solving for in these, I want you to use logarithms now instead of graphing for finding solutions. You're going to be solving these algebraically now, and I want to see exact answers and then approximate answers. Okay? So we're now going back. We're going to use solving on the word problems. Before, I just let you graph things. And there's nothing wrong with that other than graphing gives you an approximate answer every single time. Algebraically, you are able to get an exact answer. And exact is better than approximate. Okay? So, everyone's going to start. Okay, I want you to go through. Everybody do number 1. All right? I'd like you to go ahead and just see if you can get number 1 done. And we'll go over things. So get your brains moving. Your brains are moving. I'm going to check. That shouldn't be there. No, that shouldn't. Okay, let's do this problem. So just bought a brand new cell phone, decreasing in the value rate. Okay, great. So how much is it going to be worth? So my model would be y equals 849 times, you can either put 1 minus 0.18, okay, doesn't matter, or, and this is going to be raised to the t, or you could put it in here if you want 0.82, that's up to you. What's t in this problem going to be? 7, okay? So basically you're just going to evaluate, this is just a nice easy start, okay? Okay, so we're going to get in that. Now, since it's money, what will we round our money to always? If you're not told otherwise, money should be something you always round to a certain decimal place. Hundredths, 2 decimal places, because it's about pennies. 100 pennies in a dollar. Okay? So if you round this, all right, this was just a good review, what do you get?
2.
What is it?
211.64.
211.64. Do I have confirmation of that value? Yeah? Okay. There you go. Great. Okay, that's a nice, easy one to start with. All right, now, everyone write a function for number 2. And then notice what you're being asked to find on this. You're being asked to find continuous rate of change. That means you are using this model right here, because that's a continuous model. See if you can do that. Dun, dun, do, do, do. I wish there was a way. Assignment. There's got to be a way. There has to be. Okay. So using this, what's the y? What's the a value? The initial going to be on this. 14.676. Okay. So it's going to be something equals 14.676. And then that's going to be times E. We know we're trying to find R, so I know R has to be a variable in there. Now, X usually stands, if you look on here, what does X stand for? Time. this is one of the like unique ones where x is not time, but x instead is going to be what? What's that?
Distance.
What? How's it being measured though?
Miles.
You could do it in miles, okay? But then this is going to be harder down here because I'm looking ahead. This is in feet. So I'd probably be better off doing it in feet, okay? So in this particular problem, x is going to be feet. It's not time in this problem. You almost always, our exponential ones are time driven on the x. This is where they're not. This is going to be in feet instead. So for me, what do I know? At Mile High Stadium, and I told you that is 5,280 feet. Okay, the pressure is 12.2. That's the new. This now would be what you just did in the quiz, solving this. So now if I want to solve this algebraically, okay, would you please solve this algebraically now and get an exact answer for it? An exact answer for that value of R. Yes. Oh. Bum, 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 bum. One, I can make that divided by. That should give you, that would be the exact. Natural log of 12.2 over 14.676 divided by, the whole thing, divided by 5280. Okay? That's going to be the exact answer. Now, just so we can do this problem down here, we could use this as our R value. I literally could use that exact value. I don't have to round it at all then. Down here now. Okay. So there it is as an exact. Now, if I want an approximate, I should be able to do that on my calculator. What's that? 32.57. Is it 0.3257 or 32.57? 32.57. Do I have confirmation of that number? Did you, anybody else have that? I didn't do the calculations on my calculator, so let me see here. Natural log of 12.2 divided by 14.676. I don't have that. And it says if it's decaying, should R be positive or negative? Negative, right? R should be negative if this is a decay problem. I got that it's about negative 3.499, or almost basically negative 3.5. It looks like it is roughly. You have that? No?
I said it was like that, but to the E.
Oh yeah, it's scientific notation, right. Now, that's why I'm glad you said that. So if you look at, if you're using this, you'll go, oh, it's negative 3.49. Yeah, it looks like that. But what it really says is this. It's 3.49957, and then it's got an E to the negative 5. That is this on a calculator. That is scientific notation. So let's talk about that. That one, we did this way back when. That tells me to take this decimal and move it what? 5 times to the left. So that would be this. Negative 0.0000349957. Agreed? Okay, now let's say I had you do this problem. I said round it to the nearest thousands. What's happening? You would get what? 0. And then that means that I can't even use my approximation to get a good answer in the future. So we like exact answers because they're beneficial to us, because we can use them to get better answers in the future. So again, hey, if I said round it, that's just pointless then, because you wouldn't even have a rate of change then if I round it to the nearest thousand. So that's why we're going to go ahead and use the exact in our new equation down here. Okay, we're going to use the exact. So for these two problems, the model would be y equals our original, which was 14.676 times e to the, now what? This thing right here, the natural log of 12.2 over 14.676 divided by 5280. Okay. And this, you got to be very careful of this thing, guys. That's right. And then times what? Times x, where x is what? Feet. Okay. So now I've got this. Now I do know that this is what? If I want, I could just put 14.676 times this entire thing, right? Because we really know these are going to do what? Cancel each other out. So if you want, you could say it was, if somebody else wrote, well, I did this, Mr. Snyder, times, and then here I had 12.2 over 14.676 times, I'm sorry, divided by 5280, and then times x, they have the exact same thing. They have the exact same thing in the end. Okay. Now, let's go ahead and find out what's going on here now. So x is feet. So let's find out now, what's the pressure for Mr. Byer at 9,000 feet? Now we're going to use that. Oops. Oh, clear. Where in the world did that go? Calculator's not happy with me right now. Battery's almost dead. I need a different one. You guys getting an answer here? Oh, that was nice of her to drop that off. You guys getting an answer on this one? You are?
Yeah.
What'd you get?
I got 10.713.
Is that what you guys are getting? What did you have, Owen?
I had 0.71.
10.71 or 0.71?
10.7.
You had 10.71. Anybody else get an answer on this? Is anybody trying? Are you trying to do it on Desmos? I'm just kind of curious, Samuel. You're not? Okay. That sounds. It should. Let me ask you this. We know if at mile high is 5280, it better be, and that's 12.2. If I'm at 9,000, it better be less than 12.2, right? So if I'm getting an answer that's greater than 12.2, I know I've got a problem with this if you're doing this. Okay. And the hardest part here is just getting this thing even typed in probably to your calculator. You did it on Desmos? You typed it in as yeah. Just, I'm just gonna see. Did you do it on your? So you did. You kind of like used your second answer thing. Is that what you did here?
Yeah.
Yeah. Okay. So you did that. I did it because the calculator kind of stops here, and that's why you need this a little bit different. They're both. You both have right answers. I would accept either one of those. Okay. Yeah, and you did it on here. That's why. Okay. So it would be about, can you plug this in correctly, guys? So we're answer here. I'm going to just put it right here. The answer to this, when we let x equal 9,000, is about, now we'll go ahead and say an approximate 10.71 to, what did you have again, Owen? 10?
I had 10.7.
You had 10.71. What did you have again, Rick?
I I think I just made a rounding error.
Oh, okay. Well, we'll just say it's about 10.71 PSI. Okay. 10.71 PSI. All right. So here's what I'm going to ask you guys to do. Okay. I would love it if you guys would just try to work on this. Bring it back on. Let's just shoot for next Thursday. Well, I won't see you Wednesday. I don't see you Monday. We have Monday off. Wednesday, you don't come.
Probably will.
Monday night's not looking great
It's
weather-wise.
actually looking really
It looks good, exactly. So, yeah, don't lose this in the next week, basically. Okay, bring it back. And if you could have these done, that would be great. Okay? That would be fantastic. All right, I'm gonna do this. I'm gonna do that. Who'd like to live in a house like that out in the middle of nowhere? Anybody? That's me. I want to. That's what I want to retire to. When I retire, I would love that. Just out in the middle of nowhere. Okay. So I'm gonna just. Shit. Why is this not working? This and this. Here we're going to stop